So we've been looking at different operations that we can perform on signals. We've been talking about how to classify signals. In this video, we're actually going to talk about some very specific types of signals that we're going to be working with. So in this and the subsequent slides, we'll talk about some specific signals. The first one being what we call the continuous time unit impulse. So this is a specific signal that we denote by delta of t. So delta of t means something very specific in this class. And it means a signal that satisfies these criteria. First of all, it's equal to 0 everywhere except for at time 0. So it's actually equal to 0 for all time and not equal to 0. At time 0, it's actually infinitely tall and infinitely thin. So it has the property that if you integrate across it, you actually get out 1. So this is how we define what happens to the signal at time 0. We don't say really what it's equal to at that point. It's actually equal to infinity at that point. But because of how we've defined the unit impulse signal, if you integrate across it, its area turns out to be 1. So really the way to think about this continuous time unit impulse signal is it really is 0 everywhere, and the only time that it is non-zero is at time 0. At that point in time, it is infinitely tall and infinitely thin, so if you were to integrate across it, you would actually get an area of 1, but if you actually evaluate the signal at time 0, it's actually equal to infinity because it's actually infinitely tall. So what does this do? We take that information and plot what this signal looks like. This is what you see. As a function of time, the unit impulse function is 0 everywhere, so it's 0 here, it's 0 all here. The only non-zero point in time where something interesting occurs is right at time 0. At that point in time, we have a signal that is infinitely tall. Now, we can't draw something that goes up for forever. So what we do is we draw a single arrow pointing up, implying that it goes, in that direction for forever. Because it has an area of 1, when we label the kind of height, so to speak, of this signal, we can't label the height because it's infinitely tall. So what we actually put there instead is the density of that function. Remember, when we integrate across the impulse function, we get an area of 1. So this number 1 here does not mean that this arrow has a height of 1. It means if we were to integrate across it, we get an area of 1. So when you plot impulse functions, the numbers you put here aren't the typical numbers you list for other signals that really mean their height. This one here indicates that this impulse function has an area of 1. So you might be thinking, why in the world are we defining such a strange signal that's 0 everywhere except at time 0 where it's infinitely tall and infinitely thin? It turns out the impulse function, this delta of t, is very important when we start analyzing systems, when we start talking about the impulse response of the system. When we talk about the impulse response of the system, we mean the system sitting there at rest and this signal as the input. So when we put this signal as the input to our system at rest, what comes out by definition is the impulse response. So this is a very key fundamental signal that we'll be using in the rest of our class. So we've talked about the unit impulse function being this infinitely tall, infinitely thin signal. Another way of thinking about this signal is to think of it as the limiting form of a signal. So let's talk about that. Let's start over here on the left with this rectangle signal. If you look at this rectangle, epsilon is a parameter, so epsilon can be any number greater than 0. The height of this rectangle has a height of 1 over epsilon, and it has a width from minus epsilon over 2 to epsilon over 2, so that's a total width of epsilon. If I was to figure out what the area of this rectangle is, that's pretty easy to figure out. The area of a rectangle is its width times its height. So epsilon times 1 over epsilon is epsilon over epsilon, which is just 1. So no matter what value of epsilon I choose, this is a rectangle that has unit area. In the limiting form, we let epsilon get smaller and smaller and smaller. We let it go to 0. So you can see what happens as epsilon gets smaller and smaller. As epsilon gets smaller and smaller, 1 over epsilon gets bigger and bigger. So the height of this rectangle grows as epsilon gets small. And the width of this rectangle, its total width is epsilon, so its width is getting smaller and smaller. So really, if you wanted to, you could think of the impulse response as the limiting form of this rectangle function as epsilon goes to 0. And you can really do that for any signal that has the property of having unit area And in the limit, its width gets small and its height gets large. This picture over here on the right just shows another example. This rectangle has a height of 1 over epsilon, and its total width here is 2 epsilon. From minus epsilon to epsilon, that's a total distance of 2 epsilon. So if we were to compute the area of this rectangle, the area of a rectangle is 1/2 base times height. So base is 2 epsilon, height is 1 over epsilon. If you multiply those together, 2 epsilon over epsilon is 2. And then the total area is 1/2 base times height, so 1/2 times 2 is 1. So this rectangle has an area of 1 for all values of epsilon. In the limit, as epsilon gets small, this signal gets very large in amplitude, and it gets very narrow in width. So it also has the property of its height goes to infinity and its width goes to 0. So it would be fair to think of the impulse response function as being the limiting form of this as well. That's another way to think about the impulse response. So that really wraps up the key definition of the impulse function. It is a continuous time function that is 0 everywhere, but it is infinitely tall at time 0 with infinitely small width, and it has the property that if you integrate across it, you get 1. In the next full bullets, we'll explore some properties of the impulse function and also what happens if I have a continuous time function and multiply it by an impulse function, what happens.